In the 18th and 19th century, garden design became a major art form in German-speaking countries. Surprisingly, these gardens had the additional function of being vehicles to express political beliefs. Musicologist Annette Richards claims that the natural freedoms of English gardens planted the seeds of political revolutions in people's minds. Today, I hope to use these gardens to plant the seeds of understanding my engineering research. Now, before I talk about the science, let's discuss gardens. In the middle, the top row, you can see a photograph of a French garden. French gardens utilize geometric shapes to create an ordered, symmetric landscape. Now, depicted right below the French garden is an English garden. English gardens do away with the symmetry and instead randomly scatter their flora to create a natural-looking, disordered landscape. This brings me to the materials I am researching, disordered amorphous solids. The top right picture illustrates a crystalline solid where the atoms are arranged in a symmetric, ordered arrangement. Meanwhile, the bottom right picture is an amorphous solid where the atoms are disorderly arranged. Now, the freeform English garden is much cheaper and easier to design and maintain. Instead of worrying about the placement of each individual element, each piece of flora can sit comfortably anywhere in the garden's landscape. The same can be said when arranging the atoms of a solid. It is much cheaper and easier to fabricate an amorphous solid as opposed to a crystalline solid. In order to control the placement of the atoms, expensive and time-consuming methods are used to fabricate crystalline solids. For example, the solids are fabricated in hot environments as high as 500 degrees Celsius to ensure that the atoms have enough kinetic energy to move themselves into a crystalline formation. Additionally, these crystalline materials are often made on top of expensive pre-existing crystals such as sapphire. This provides the atoms with a crystalline template to encourage the formation of an ordered crystalline pattern. Historically, crystalline materials have had the spotlight in the research of solids. It has been strongly believed that ordered symmetry is required to accurately model and predict the behavior of electricity and electrons in a solid. My research aims to show that amorphous materials can be just as effective, if not better, than crystalline materials whilst being cheaper to manufacture. These materials have the potential to revolutionize low-energy electronics. I hope in the future the design and the structure of our solids can be as carefree and disordered as the English garden.